Hello, everyone, and welcome to this online event in-vehicle acoustic test according to AES recommendations with grass, sound and vibration and audio precision, two of the brands of Axiometric solutions. My name is Teresa Rubio, and in today's online event, I would like to introduce you to James Kelly, Regional Manager at Support and Applications at Grass and Audio Precision. Welcome. Before we begin, I want to cover a few housekeeping items. At the moment, you are all muted. During the event, you can submit your questions through the questions section on your screen. We will try to answer these questions afterwards in the Q&A session. And if we run out of time or a longer explanation is required, we will follow up after the event via email. After the event, you will see a survey that we would really like you to answer, and it won't take you more than 2 minutes. Lastly, an on-demand version of today's event will be also sent next week, so you will be able to watch this event again. And without further ado, I would like to pass the word to James Kelly.
Okay, thanks, Teresa. Okay, so I hope you can all see my screen, my presentation. As Teresa said, my name is James Kelly. I'm the regional manager in support and applications for AP and Grass. I'm based in the UK, but travel worldwide, visiting customers and carrying out training. So let's jump straight into this. So the Audio Engineering Society have created a technical committee on automotive audio. This was created in February 2020, and they could see some shortcomings within in-car acoustic measurements, and most manufacturers and OEMs, tier 1 suppliers, etc., were all doing measurements themselves, but there was no continuity between these. They were all doing different measurements and using different equipment. So the motivation for some of the measurements, frequency response, the most common measurement within the audio industry, reveals basic properties of the system, and it gives you a quick visual check of the spectral balance of the audio system in the car. Max SPL is an important in system level specs, and it's easy to compare between systems. It puts demands on loudspeakers, amplifiers, power supplies, and system integration. And then impulsive distortion. So impulsive distortion, or rub and buzz, extraneous noise, squeak and rattle, for example, is something that would be common to people making loudspeakers. But in a car, it can be very important, just because there's a lot of opportunity for additional rub and buzz, not just from loudspeakers. Things like loose door panels, loose switches, perhaps for electric windows or something. All of these can add to rub and buzz. So typically in a vehicle, there's lots of things to measure. Things like road noise, wind noise, inverter noise in electric vehicles, audio system acoustic characterization, audio system design, tuning, so good listening experience from every seat. This is something typically that all manufacturers are doing already. Audio system electronics, so audio amplifiers, crossovers, etc., will be measured. Sound quality of car alarms, doors closing, engine sound, even things like the indicator noises that you hear inside a vehicle now. Long gone are the days where it was an actual relay clicking. Infotainment, so smart assistant, Bluetooth audio, telecoms, car microphones, so all of these will be measured. But the AES recommendation is specifically looking at audio system acoustic characterization. So in the cabin interior, we don't have a free field, we don't have a pressure field, and we don't have a diffuse field. We have something which is neither of these. And we measure this with measurement microphones, but based in an array. So a 6 microphone array, which was derived from a number of microphones. And you can see on the screen now that there were studies going back to 1986 on this. And really, they started off, or they determined that 18 discrete microphone points anchored at the 5th, 50th and 95th percentile locations in the range of head positions was an effective method. Further, they were able to establish acceptable limits from 6 strategically chosen microphones from the 18, gave sufficiently accurate results. So I've highlighted this part of the recommendation, saying it's preferably to average the pressure squared, i.e. power average, just because that's an easy derived result to apply within APX 500. So looking at the microphones, we'll take a look at what happens when you actually place a microphone in the sound field. So the microphone actually disturbs the sound field that it's trying to measure. And the larger the microphone, the bigger the object. So it's not just the microphone, can be the stand, the H array itself. And there's some important factors relating to that, which I'll discuss later. This will disturb the sound field. So much of the time, a free field microphone has been used for this purpose, for measuring in-car acoustics. Now, free field microphone is optimized to work in a free field environment, an anechoic chamber, for example, which is certainly not the case inside a vehicle. So there's an animation here showing the effects of placing a microphone inside the sound field and typically what happens. And we can see 2 instances here, one using a 1/2 inch microphone and one using a 1/4 inch microphone. And you can see the effect on the graph in the middle of the screen here. The difference between a 1/2 inch microphone and a 1/4 inch microphone. And effectively, the disturbance on a smaller object such as the 1/4 inch microphone is moved up to higher frequencies outside the range of human hearing. So the bigger the object is, the bigger the influence in the sound field. Smaller objects will move the influence to the sound field to higher frequencies, as I just mentioned. So we normally choose different microphones for different sound fields. So pressure microphones for a pressure sound field, typically mounted in a surface. A free field microphone, typically used in anechoic chambers or other free field environments. Or a diffuse field microphone, typically used in a reverberation room where you have a consistent diffused field with sound coming from equally from all directions. But the car cabin is none of these. It's something else. So what do we do? So the first problem is when we want to use a 1/4-inch microphone, so it has less influence on the sound field, we have a problem because typically 1/4-inch microphones have a higher noise floor than the traditional 1/2-inch microphones. So it's great that it moves the disturbance to higher frequencies, but we have this higher noise floor. So 44 dBA total noise is a typical spec for a 1/4-inch microphone. So Grass have taken it upon themselves and developed 2 new microphones with a much lower noise floor. So typically something that's comparable to a 1/2-inch microphone. So here you can see total noise of 24 dBA. And this is the issue if you just use a 1/4-inch microphone. So there's an example here of inverter noise that couldn't be measured with a traditional 1/4-inch microphone, but is easily measured with the 2 new 1/4-inch microphones that have been designed specifically for in-car acoustics. So 2 new Grass microphones, 46BL-1, a pressure mic with a frequency range of 4 Hz to 20 kHz, dynamic range 24 dBA to 145 dB, and sensitivity of 20 millivolts per Pascal. So meeting everything as per the recommendation from the AES. And then we've got another microphone, the 46BC. It's not a pressure microphone, it's not a free field microphone, and it's not a diffuse field microphone. It's something which we're calling a multi-field microphone. It has very similar specs to the 46BL-1, but it has some unique features which we will look at shortly. So we know 1/4-inch mics reduce uncertainty because they have less effect on the sound field. Regular 1/4-inch mics are still optimized for ideal sound fields, and even the 46BL-1 is optimized for a pressure field. But that's what the AES are recommending is used in this application. So typically they'll be optimized for pressure, diffused or free field. And then, yeah, what if we're working in a car cabin, which is none of these? So what do we do? And this is where we take a look at our multi-field mic, the 46BC. You can see it meets the IEC 61672 limits for every type of field. So it's maximum response with any type of sound field is within the limits, and its minimum response with any type of sound field is within the limits. So this reduces the uncertainty, and also every acoustic measurement, and especially where we're using a microphone in a sound field which it's not been optimized for, such as this, is going to have errors. Now there's an argument to say that errors will be consistent, but with a 46BC, those errors are minimized, so the data is more accurate. So typically, and we know this has been a the case for many automotive manufacturers. They will be using a free field microphone inside a cabin. And you can see that a free field microphone doesn't even meet the IEC 61672 limits in all sound fields. So it will be perfectly flat in a free field environment, but not for a pressure field or for a diffuse field. So that causes an issue in a vehicle, and it also increases the amount of error and the uncertainty of the measurement. So this is a typical setup for measuring in vehicle for the AES recommendation. Here we've got a multi-channel audio precision analyzer. We have two Grass 12BB power supplies, and these are connected to our 6-channel H-array microphone array, and a PC running APX 500 software. And we have a number of measurements that we'll be using and derived results, which I will talk through shortly. So you don't have to have a multi-channel analyzer. It certainly helps. It makes the process faster and perhaps more consistent. You know that the data is acquired simultaneously, but you can have other test setups using other AP analyzers and also using our Flex analyzer with some ASIO sound cards. And here on screen, you can see some options. And we've created project files for all of these options. We have a project file for the Flex using the RME UCX2. We have options with 2-channel analyzers, the APX 555, for example, and both with using our AP switchers, so it can be totally automated. But there's also sequences in the project files which prompt you to move connections to individual microphones. And we have the same for an APX 517, for example. So using the APX 500 software with prompts, derived results, and our built-in measurement navigator and sequencer, it's quite easy to create sequences of measurements to meet the AES recommendation. So here we're going to talk through how we've achieved this for some of their recommended measurements. So for the AES LEQA requirement, we use a noise recorder and a derived result on a derived result. So we actually prompt the user to play a certain pink noise source provided by AES with a specific crest factor. And we wait 5 seconds as per their recommendation for the cabin to stabilize. We then run the noise recorder for 30 seconds, again, as per their recommendation. This will give us 6 channels of RMS noise level over 30 seconds. And this is A-weighted, again, as per their recommendations. We then power average this from all 6 channels to effectively give us an average on a single trace. And then from that, we derive again a single value to give us a figure that we're aiming for, in this case 80 dB SPL. So this sets our volume for subsequent measurements. So such as the response, again using pink noise. And to do this, we use the signal analyzer, running FFT, again over 30 seconds. And we use the power spectral density result, and we add a derived result to that for the octave spectrum. So 1/3 octave as suggested by the AES recommendation. And then we power average that from all 6 channels to give us again 1 trace for the response. For impulsive distortion, we use a log chirp sweep, and we use several different results. So we have our RMS level, which you can see here with the blue line, and we can also see it here with the blue line. We then have our rub and buzz peak ratio, which is, as per the standard, our impulsive distortion. But this can't be shown on the same scale as RMS level. So it's not in dBSPL, as it's a ratio. We also have our crest factor, which again is a good indication of any rub and buzz, squeak, rattles, etc. So what we've added here is a high order harmonic distortion. So this is our impulsive distortion result in comparison to the RMS level. And it's really the difference of this average level here and the maximum point on the high order harmonics, which indicates how good the acoustics is within the vehicle, or at least how much it's influenced by any rub and buzz. So using sequence steps, variables and input techniques, a project file can easily be created. So for example, here you can see a prompt to enter a make and model of a vehicle, and this will be recorded in the report. Another prompt here on placing the H array in the vehicle as recommended by the AES. I should mention that this AES recommendation is evolving. I've just got back from AES Automotive in Gothenburg, where there were several presentations based on this recommendation, and as a result, I'm sure this is due to change, because for example, if you try and do this in a Ferrari, you cannot place the H array as recommended by the AES, because it effectively there's not enough room before the microphones are touching the interior roof of the car. Now here's another prompt telling you to play the pink noise track as provided by the AES and adjust the volume for a certain target level. So again, typical setup for a demonstration would be this, and even though that's a very small car, I don't have the facilities to do that live during this presentation. So I'm going to play a video and talk through what's happening in the video, running through the measurements. So first things first, I open the project that I'm using. Here I was lucky enough to have an APX 585 with the H array and 2 Grass 12BB power modules. And these were straight from the factory. So you'll hopefully see on the screen when I use the drop down to choose a sequence, I'm going to choose calibrate from TEDS just because it's so quick. So when I run this, it will read the sensitivity from each of the 6 microphones and apply it into the APX 500 software. There is a sequence to manually calibrate the 6 microphones using an external calibrator. So this reads all 6 sensitivities and applies it to the signal path, as can be seen. And those references, those sensitivities are copied across to the signal path that we use for the in-car acoustics using a sequence step. Now for the in-car acoustics, I'm not selecting all of the measurements. The environment I had wasn't able to measure down to 50 dB SPL or even 60 dB SPL. So I include 70 dB SPL. 80 is our starting point as recommended by AES. And then I do 90 and max SPL. So here you can see the prompts prompting me to place the array in the vehicle. In reality, this had already been done. And then to play a track. Now, this could be automated in APX using something like the Bluetooth Duo module, but not everybody has that available to them. So I thought it was best left as an open loop measurement. And you can use a USB, you can use CarPlay, Android Auto, or Bluetooth, so from a mobile. And Bluetooth is quite convenient on a mobile because it means you can stand outside the vehicle. So here you can see we're waiting our mandatory 5 seconds, and then we're acquiring the data. In the film strip at the bottom of this metered graph result, you can hopefully see RMS level being acquired for 6 channels over 30 seconds, and then derived into a single trace, and then again derived into a single value, which we're looking at live, updating it in the video. So we do this for 30 seconds to achieve our LEQ-A, so A-weighted result. And then we use the same source to measure our response. And we're doing this with our 30 averages and deriving our octave spectrum. So we have 6 channels of octave spectrum next to our single trace, which you can see on the screen. And all of these are within the projects that will be available to download sometime next week at the same time you get your email to download the video of this presentation. Then there's a prompt to basically stop playing that file. You can press OK, and we use our open loop chirp measurement. So we have a pilot tone. I've chosen a 4 kilohertz pilot tone because it's outside of the frequency range of the log chirp. So I wanted something which was different to the frequency used in the log chirp, and then it obtains our RMS level response and high order harmonics, as well as peak ratio and crest factor for rub and buzz. We then repeat this process for as many of the other levels that can be obtained in the environment you're measuring in. And you'll see here again, I'm adjusting the volume for now 70 dB SPL. So most mobile phones, obviously you can use the volume up and down to achieve this, but they also usually have an option where you can get a more detailed view of the level, which you can typically swipe across with your finger. So you can see here I'm struggling to get 70 dB SPL, but I do get there in the end, you'll see. You can see as well I've been a little lazy. Rather than type in Bluetooth, I've just typed in BT. But as long as the user knows what they mean, that's fine. Some little tips. When I was creating this project file, typically any of those prompts have a 30-second or 60-second timeout. And I found that wasn't adequate for some of these options. So I removed the timeout feature on many of these prompts. So here again, we're doing the LEQ for 70 dB SPL, again using the pink noise. Here we're waiting, and then we're acquiring the data using our signal analyzer, and then deriving from power spectral density our 6 channels of octave spectrum, 1/3 octave as recommended, and then deriving that again into a single trace to get the overall response, spatially averaged response. Again, the same prompt to stop that pink noise, press OK, and then play the open loop chirp. And again, the chirp is provided by AES, and you can prepend a pilot tone if required. So just a point if you're not using APX and you still want to do this with something else, it's something you might need to do if you're doing open loop measurements. So now you can see we're going to do this again for 90 dB SPL. And at the end of this, you'll be presented with a report with all of these results and all of the data, such as the make and model of the car, the input you're using for each measurement, recorded in the report. And you can possibly appreciate as well that what you're seeing here is 6 channels of simultaneous acquisition. In the project files, for example, that are only measuring 2 channels at a time, you'll have to factor in that this is going to take at least 3 times longer for each of these measurements. So certainly if you have 6 channel acquisition, whether it's a multi-channel APX or whether it's a ASIO device, it has its benefits. So again, we do the open loop chirp. and we get our RMS level and our response. And then we set the volume to maximum. We do our max SPL. And as you can see here, 94 dB SPL was about as much as I could get in this vehicle. And again, we get our response at maximum using the pink noise. And the report that's generated at the end of the sequence. You can see the results. You'll see the sensitivity of each microphone. And then you'll see some of the graph results, including the 6 channels of octave spectrum and then the power averaged result to give us our frequency response. And then our RMS level and high order harmonic distortion, and so on. So that's all I have today. I'd like to open up the webinar for questions using the questions field in the webinar. And I can see I have one question. Someone's asked, is there a way to repeat the sequence while updating the seat label, e.g. driver, passenger, rear left, etc.? So if I show my screen, let me hopefully you can see my software now. For example, we have our pre-sequence steps and we have a device ID prompt here. And this is where we ask the user to enter the make and model of the vehicle. You can add a new variable, which could be seat ID, for example. And you could enter that. This could be seat position. And if we preview that now, we should have 2 fields. So in here, we can enter make and model of vehicle. Then we can do enter seat position of H array. Now, in our reports, we can automatically save that, and we can use that variable to either name the report or even create a folder for each different seat, for example. Or we could, if required, let's say we want to export some data, we can add a step to either export a WAV file or export the result data. Choose, for example, RMS level, power average, Robin buzz peak ratio, or any of the results that you're interested in can be exported, can be given either a path or a name using the variables. So we could create a folder, subfolder here, using device ID, and then another subfolder if required, using the seat ID. And you can even, if you really wanted to, add the source as well into this, and you can save this as a Acoustic response, or you could save it as, I don't know, impulsive distortion. That could even be the name of the Excel file, or it could be, as I say, a subfolder. So that's how you could easily modify this to include seat positions, automatically name reports, or automatically export data based on seat position and make and model of the vehicle. As I say, this is a recommendation. This is an evolving recommendation, which is likely to become an AES standard in the future. But at the moment, it's just a recommendation. And as such, I'm sure these project files will evolve as the recommendation evolves. Lots of committee meetings, lots of events worldwide to talk about this recommendation and how they move forward. I'm not going to save that. So, any other questions? I can't see any in the questions box. So, in that case, I think we're finished.
Thank you, James, for your excellent presentation. And thank you also to our audience for your participation. You will please to know, as we said at the beginning, that an on-demand version of today's event will be sent to the email address that you register within a week. And after the event, you will be prompted to a survey. So we would like to know your opinion, and it won't take more than a minute. If you have any questions, you can see that you can send us an email to marketing@grassacoustic.com, support@grassacoustic.com, or tech support@ap.com. Have a nice day, everyone, and we look forward to the next time. Bye-bye.
Thanks, everyone. Bye-bye.
Bye.